Well, hello. I'm Colleen from Mom Teaches Tech, and I can see that you're here to learn today, and I love that for both of us. To combat the OSPF overload, I just want you to pretend that there's only one type of OSPF, and that type is Single-Area OSPF v2 in a point-to-point network configuration. For those of you who are aware that the other OSPF versions and configurations exist, I just want you to ignore all of those for now and return to an imaginary time and space where you only need to know the details about single area OSPF v2, where routers are connected by a point-to-point configuration. I have represented this imaginary, simple idea with a little island here, which is the area 0 to be precise, and a house representing a router, and then we'll draw in another router / house here, and these are our point-to-point connected routers.
OSPF is a link state routing protocol.
Okay, that was my attempt at a very monotone voice. So this phrase is one of the most common things you may hear or read when learning about OSPF. And it's exactly the point where your eyes probably begin to glaze over. OSPF stands for Open Shortest Path First. As I said before, there are a few flavors of OSPF. For now, we'll just be working with OSPF v2, which is commonly referred to as just plain OSPF. OSPF v2 does not support IPv6, but it is still one of the most widely used routing protocols and very important for you to learn. It is an open standard and scales extremely well, meaning that as your network grows, so too can OSPF. Another important thing to remember is that we are talking about dynamic routing. Dynamic routing protocols automatically learn, update, and adapt routing paths in response to network changes, allowing routers to make efficient forwarding decisions without manual intervention. One question that sometimes turns up in Cisco exams or the CCNA exam revolves around the algorithms that are used to calculate the various dynamic routing protocols. And so you should know that OSPF uses, and I'm going to try not to botch this name, Edgar-Dijkstra's shortest path first, commonly referred to as the SPF algorithm. As a side note, I had to learn Dijkstra's algorithm or the SPF algorithm for a math class, and it was sort of the best part of that math class, which I did not tell my instructor, but I hope he continued to teach it. If you watched my video about dynamic routing, hopefully you remember hearing about link state routing decisions. For some practical exam questions, you'll often see it phrased like this: which routing protocol allows routers to share information about their links so that all routers build the same network map? Which routing protocol does not rely on neighbors' routing tables to make routing decisions? Or this very straightforward question: which routing protocol uses a link state approach rather than a distance vector approach to routing? In all of these cases, the answer is OSPF. Hello packets are key to OSPF operations. OSPF routers use hello packets to discover other routers on the network and to maintain their relationships. For hello packets to be exchanged, there are certain interface requirements. The interface must be an active OSPF-enabled interface. Let's discuss hello packets and initial communication. When a router receives an OSPF hello packet, it doesn't automatically respond. Instead, the receiving router checks the parameters inside the hello packet to make sure they match its own settings. These include the area ID, that the routers are on the same network, the hello timer, the dead timer, and the network type such as point-to-point or broadcast. If all of these parameters match, the receiving router sends a hello packet back. That exchange is what allows the routers to recognize each other as potential neighbors. I slipped in 2 new terms that you may not have heard before on that last slide, the hello timer and the dead timer. That was very sneaky of me. I have my cute little capybaras here representing hello and dead timers for you. We all know that the dead capybara is just a great actor and he isn't actually dead, but your router interface doesn't really sleep. So if it's dead, it's probably down or administratively down, or someone removed the wrong cable. Things can really go wrong here. That's what the dead timer is for. But back to the hello timer first. The hello timer controls how often a router sends hello packets out of an OSPF enabled interface. Back to our little island where we have just a point-to-point connection. Hello packets are sent out every 10 seconds. These hello packets are sent to the multicast address 224.0.0.5, which stands for all SPF routers, often a test question. The dead timer, as demonstrated by our sleeping capybara, controls how long a router will wait to hear a hello packet from a neighbor router. In a point-to-point OSPF topology, the dead timer is 40 seconds by default. If a router does not receive a hello packet from a neighbor within the dead timer interval, the neighbor relationship is considered down, and the router removes that neighbor from its OSPF database. You might be thinking back a couple of slides and asking yourself, what happens if the area ID, network type, or another required parameter doesn't match? That's a good question. When required OSPF parameters do not match, the routers do not form a neighbor relationship. However, the routers do continue sending hello packets out of their OSPF-enabled interfaces. In a point-to-point OSPF network, those hello packets are sent to the multicast address what? If you answered 224.0.0.5, also known as all SPF routers, you are correct. Because no neighbor relationship exists, these routers here that are in different networks, they remain in what is called the INIT state. Importantly, all OSPF neighbor relationships start in the INIT state. Even when every parameter matches, routers must pass through the init state before moving forward. Think of init as the word initial. It's the starting point that must occur before OSPF can begin forming neighbor relationships. Now that we understand the init state as the initial exchange of hello packets, you might be wondering, is there a specific name for the state routers enter when the required hello parameters do match? Why, yes, there is. When all required parameters match, the next step in the OSPF process is the two-way state. Here's what happens. Once the parameters match, each router begins including the router ID of the other router in its hello packets. When a router receives a hello packet and sees its own router ID listed, the routers transition into the two-way state. At this point, the routers have successfully discovered each other and are officially considered OSPF neighbors. Even after the two-way state is established, hello packets continue to play an important role. They are used to maintain the neighbor relationship. You can think of the hello and dead timers as a heartbeat system. Hello packets say, "I'm still here." The dead timer asks, "How long will I wait before assuming you're gone?" As long as the hello packets arrive before the dead timer expires, the neighbor relationship stays up. Now, these default values, such as the 10-second hello timer and the 40-second dead timer, may not always be ideal. While your routers don't actually get annoyed, your network might. And in some environments, 10 seconds is too slow to detect a failure, and 40 seconds is far too long to wait if a critical link goes down. The good news is that these values are fully configurable to meet your network needs, but you do need to memorize the default times for this point-to-point network. This has been a lot to cover, and at this point we've introduced several new terms and concepts, including hello packets, hello timers, dead timers, INIT state, two-way state, OSPF neighbors. And before we move on to the next OSPF video, I snuck in one other little item, the router ID. I don't know if you noticed that. I snuck it in the previous slide there. So we've got to cover the router ID. In OSPF, every router must have a router ID which uniquely identifies that router within the OSPF domain. You've already seen that routers must include their neighbor's router ID in a hello packet in order to move from the init state to the two-way state. So that raises an obvious question. Where does the router ID come from? Did a capybara magically assign it? No, a capybara doesn't even know what a router ID looks like. But do you know what a router ID looks like? A router ID is written in dotted decimal format, which should look very familiar to you. However, it does not have to be a real IP address. It's written like an IP address, but it is not used for addressing. Any value from 1.1.1.1 to 255.255.255.255 is a valid router ID. Now, onto this adorable little router here and how it determines its router ID. There are 3 ways that a router can determine its router ID, and OSPF follows a very specific order when making this decision. And you, my friend, need to memorize this order. Option 1 is a manually configured router ID, which is given the highest priority. What does it mean that this is the highest priority? Well, if you configure a router ID on your router, then that is what the router will use for its OSPF processes. The router will not look for another way to determine its router ID. If a router ID is manually configured, OSPF will always use it regardless of interface or loopback addresses. In our example here, we've gone into router OSPF1 and we use the router-ID keyword, and here we've given this router a 3.3.3.3 router ID. OSPF is designed to make up its own router ID if you don't do that step. So the first way the router can figure out its own router ID is with option 2 here. The router will look for the highest loopback IP address if no router ID is manually configured. Some network engineers prefer loopbacks to manually configured router IDs, and that's because loopbacks are a software interface that is always up. So some people will intentionally not configure the router ID as was done in option 1, and they will purposefully want the router to use a loopback that has been configured on the router instead. Finally, we have option 3. The OSPF process will pick the highest IP address on an active interface. This sort of makes it foolproof for OSPF to have a router ID, but it's not considered the most desirable way to get the router ID. For example, if our adorable little router here has 10.0.0.1 /24, let's just go with /24 for these. So 10.0.0.1, 192.168.0.1, and 192.168.10.1, the router ID, and there's no router ID explicitly configured, and there's no loopback configured, then the router ID would be 192.168.10.1. You've learned that the router ID is included in Hello packets, and it's used to establish the neighbor relationship, allowing routers to reach a two-way state. I want you to pause here and see what you can remember. No rewinding. If any of these concepts are fuzzy, review those concepts. This is just the start of OSPF. It's good to build this foundation now, and in future videos we're going to build on this foundation in a step-by-step manner that I hope you find helpful. I hope this made sense for you, and if it did, well then we're winning. Check back weekly for new videos, or so I hope. I have kept up my pace for 1 whole week, and so there's hope that I will be posting a video weekly. If you are hanging on the edge of your seat waiting to see another capybara, go ahead and subscribe if you would. That would be great. You could also comment and let me know if this was helpful or if you'd liked something different, because I'm not saying that I'll do anything different, but I might if it's a good suggestion. I hope to see you next time. Bye-bye for now.